Now, let's talk about magnitudes. So, in 129 BC, the Greek astronomer Hipparchus published a catalog, and in this catalog, he made the somewhat fateful decision that he was going to call the brightest stars that he could see with his own eye first magnitude, and the faintest stars he was going to call sixth magnitude. And he put the stars in bins between first and sixth magnitude, in that fashion. So then some years later, 140 AD, Ptolemy copied this system. And then Ptolemy became the basic astronomy text for the next 1400 years. So we are irrevocably stuck now with big numbers meaning fainter things. So blame Hipparchus or Ptolemy for this system. So I flashed this slide up earlier, but these are eight different stars showing you the range in brightnesses for these different magnitude stars. So first magnitude, second, third, fourth, fifth, and sixth. We got 0th magnitude and minus 1.44. You see, bright stars have negative numbers for stellar magnitude. The actual stars that they are listed there. But that's the idea. Brighter stars have smaller numbers. Fainter stars have bigger numbers. Now, the other thing to note in here is what we were talking about a couple movies ago, which is even though that star looks bigger and this one looks smaller, they're not actually bigger. They're all point sources because the point spread functions for all of these are identical. They're just different in amplitude. So it's not that they're bigger, they're just brighter. Okay. Now, the quantitative definition of a magnitude is as follows. A magnitude is actually a flux ratio. This first equation here is the definition of a magnitude. So the magnitude of one star minus the magnitude of another star in the same band is equal to 2.5 times the log base 10 of the ratio of the fluxes. Now look, M2, F2. That's how you get smaller numbers being brighter stars. The magnitude system in the optical was defined to be referenced to Vega. In other words, the flux from Vega is defined to be 0 magnitude. So that means then it's stuffing Vega in for star 2. Because Vega is defined to be 0 magnitude, then M2 is 0. And then F2 is the flux of Vega. So you get M is equal to 2.5 times the log of F Vega over the flux of your star that you're trying to measure. Now, things are going to get complicated when you go into the infrared. Because when they looked at Vega with IRAS, they discovered that it did not look like what they expected. And in fact, it has a fairly large infrared excess. Therefore, infrared magnitudes are defined with respect to what Vega would be if it didn't have an excess, which ends up making calibration of infrared magnitudes a little bit squishier than people would like, but that's the reality. That's just the way it works. So remember, of course, stars are going to get fainter when you move them further away. So apparent magnitude is the brightness an object appears to us to have from our position here on Earth, given the actual physical location of the star. Absolute magnitude is the brightness an object would have if we could move it to a quote-unquote standard distance of 10 parsecs. And a parsec is 3.26 light years. So that formula then is m minus m, so apparent magnitude minus the absolute magnitude, is 5 times the log base 10 of the distance in parsecs minus 5. So m minus m is 5 log d minus 5. Again, further away is fainter, so that means larger numbers. Okay. One slide on units. Now, flux densities, which sometimes people get sloppy and just call fluxes, are energy per unit area, per unit time, per photon. So that can be like ergs per centimeter squared, per second, per hertz, or per centimeter for wavelength. Brighter sources have bigger numbers for flux densities. And flux densities are linear units. That means that something that has a flux density twice as much as something else is twice as bright. Okay. When we make spectral energy distributions, SEDs, those are energy densities. So you need energy per photon. So you need to convert flux densities or magnitudes into energy densities before plotting in SED. These plots of energy densities should be log-log plots. Magnitudes are implicitly flux ratios, and they are somewhat counterintuitively backwards in that brighter sources have smaller numbers. And they are logarithmic units. In other words, something at 5th magnitude is not twice as bright as something at 10th magnitude. It is 100 times brighter than something at 10th magnitude. You might want to write all this down, take a screen snapshot, something. Okay, maybe there's 2 slides on units. Making things even more confusing, if you are working with Pan-STARRS data or Sloan data, SDSS's Sloan Digital Sky Survey, they have a slightly different scheme. The Sloan Digital Sky Surveys came first, and the people that were working on that survey mostly study galaxies. Pan-STARRS is a newer survey, but it builds upon the work started by SDSS. All of these extragalactic folk decided that they didn't want to define their measurement system based on a star because they study galaxies. So they wanted to calculate magnitudes with respect to a flat spectrum, not a stellar blackbody spectrum. So they are called AB magnitudes rather than Vega magnitudes. And so for that definition, instead of the Vega flux in the definition of magnitude, you use 3631 Janskis for any band you care to use. It is always 3631 Janskis for an AB magnitude. This makes a huge difference in terms of where things appear in plots, what colors you expect to see from a star, and everything else. I am sorry about this strange units. I hate AB magnitudes too. It's just the way that it works. It's, like inches, meters, and furlongs. It's just another unit of measuring brightness. If you are in a situation where they haven't told you for sure whether it's a Vega magnitude or an AB magnitude, you can probably safely assume it's Vega-based, but you should check and make sure. You should check the documentation for whatever survey or paper you're working with to try to make sure that it's a Vega magnitude and not an AB magnitude. Okay, now if you measure the magnitude or any other object in a band, if it's calibrated, which it should be, because if you're measuring magnitudes, they should be calibrated, implicitly you are comparing to Vega. But if you measure the magnitude of a star or any other object in 2 different bands, 2 different wavelengths, and compare them, then the Vega flux cancels out. So again, that's a definition of magnitudes. So if I've got the measurement of a star at B band and a measurement of a star at V band, so I can do the B band minus the V band is equal to 2.5 times the log of the flux of the star at V over the flux of the star at B. So the color, which is the difference of 2 magnitudes, which is conventionally a shorter wavelength band minus the longer wavelength band, is actually a ratio of the fluxes. Okay? So it is often very, very useful to take the same object and compare its brightness at 2 different bands. It is easiest to do that as a ratio of flux densities, in other words, a difference of magnitudes. Conventionally, it's always blue or minus redder. So B minus V, J minus K, IRAC 1 minus IRAC 4, K minus 24. It's always got to be blue or minus redder. That way, if you stick to that convention, then larger numbers of color is always going to be red and smaller numbers are always going to be blue. If you don't construct the color that way, then all bets are off. If you have a red star, by which I mean a star that is brighter in red than other colors of light, it doesn't matter how far away it is from you, it's still red. It's going to be red if it's close, it's going to be red if it's far away. That means that the ratio of red to blue is something that's not going to change with distance. So its color will not change with distance. But if this, because that, if the color isn't going to change, right? Because if it's further away, it's fainter in blue and fainter in red. So the ratio of intensities doesn't change with distance. But what does change the color is the temperature. Things are going to get hotter when they get bluer, or things get bluer when they get hotter. There's a causality, or however you want to think of that. If something's bluer, then it's hotter, or if you're going to make something hotter, then it gets bluer. So the takeaway points from this chapter are those two definitions: that implicitly magnitudes are flux ratios, and that smaller numbers are brighter sources. They are logarithmic, and that something at 5th magnitude is 100 times brighter than something at 10th magnitude. AB magnitudes are different than vega magnitudes. Colors are differences of magnitudes and therefore are flux ratios. Magnitudes depend on distance. Colors do not. Colors are independent of distance. And colors should always be the bluer band minus the redder band. Okay?